Hi everyone, my name is Sandra Hirche and it is my pleasure to present our work as Keynote for the Rapid Interactive session here at ACC 2020. This talk is about online learning for control and how the anticipation of learning may improve control performance in the long term. This research has been performed mainly by PhD candidate Alexandre Capone and myself. Whenever systems are highly uncertain, learning control is a promising approach. Our research in this area is motivated by human-machine interaction, as for example robotic rehabilitation as illustrated on the left, and closed-loop deep brain stimulation as illustrated on the right. These systems comprise highly complex but unknown dynamics, which are difficult to model from first-order principles. Furthermore, in human-centric and many other applications, offline learning is not an option. So the question is, how to design controllers that learn online in order to improve the control performance. Learning control is a rich and rapidly growing field which has seen a reconnaissance due to the advances in machine learning. In this talk, we are concerned with the setting illustrated here on the right. The system is largely uncertain as indicated by the gray shaded area. The little available knowledge is represented by the white areas with the blue crosses. The objective for the control is to drive the system from the initial state x0 to the goal state. Obviously, control must navigate them through an uncertain space. There are essentially three control paradigms to address this problem. The so-called offline methods design the controller with a priori collected data. This is the most standard technique where system identification and control is separately executed. But also some reinforcement learning approaches fall into this category. Yet, if the model uncertainty is too high, control may easily fail. The second category spans all approaches where the controller is updated online during operation. Most classical adaptive control approaches fall into this category. Yet the learning there happens in a passive fashion, while the controller merely tries to reach the control objective and exploration happens only accidentally. As a result, the closed loop has a potentially poor performance. The controller in a third category attempts to simultaneously explore and exploit, such that the overall goal is reached robustly with high performance. This is also known as dual control. The idea of dual control has been around for quite some time by now. However, in the light of advanced learning techniques, in particular with non-parametric models, there arise new challenges, which we will consider in this talk. Let's have a look at the problem in a more formal way. We consider nonlinear dynamics with unknown part G. In this talk, we assume that G is represented by a non-parametric model, a Gaussian process, in short, GP. We consider an online learning control law where the data is collected to learn about the unknown G and thereby improve the control. As an example, G is directly learned in a model-based control law. The objective is to design a theta parameterized feedback policy which minimizes the expected finite horizon cost. Here, the expectation is taken with respect to all possible realizations of the unknown function G, which is represented by a probabilistic model, our GP. Solving the stochastic problem is computationally prohibitive. In order to reduce computational complexity, in this talk we present a sampling-based approximation technique, which is called sample average approximation. We combine it with Gaussian process dynamical models and show that the approximate solution converges to the true solution of the optimization problem. To this end, we will also need to predict the system behavior over multiple time steps. And we will see that the multi-step prediction for GP dynamical models is non-trivial. Let us first look at the uncertainty description via a Gaussian process. GPs belong to the class of probabilistic non-parametric models. A GP is a collection of random variables of which any finite subset is jointly normally distributed. On the left-hand side, you see a GP regression based on three training data pairs. The blue line describes the mean function. The shadowed area describes the standard deviation of the prediction for a test input. You can observe that it increases with distance to training data. In fact, a GP represents a distribution over functions, and on the right-hand side you see possible function samples, which are all compatible with the GP description on the left. GPs have become quite popular as they have a rich function space and they naturally quantify epistemic model uncertainty. One of the main limitations is scalability with respect to the number of training data points. There are some promising advances towards real-time regression, but still GPs are clearly better suited for sparse data regimes. In our problem setting, we assume that the unknown function g is drawn from a GP. In contrast to classical regression, this constitutes a Gaussian process dynamical model now, as the GP maps from one to the next step of the state. Now consider we would like to predict the state evolution starting from this normally distributed x0. The probability distribution of x1 depends on x0 as expected. But x1 is now the input to the GP and the output x2 depends on both x0 and x1. In fact, the probability distribution at time t depends on all previous states, hence results in a non-Markovian dynamics. This makes it non-trivial for analysis and also computation. For the multi-step prediction in this work, we employ an equivalent formulation of the GP dynamical model, which makes it compatible with the later application of the sampling-based optimization algorithm. Here we leverage the fact that the conditional distribution on the previous data is still Gaussian. The dynamics is driven by an IID noise sequence theta, and the mu and the sigma here represent the mean and variance, which depend non-linearly on a whole state sequence up to the point t. Hence, here we employ the ideal version of the multi-step prediction. Using the whole history of data for the prediction for the next step is possible only for limited time horizons. So for the sake of completeness, we would like to point out that there are various approximation techniques to reduce the computational demands of the multi-step prediction. Here on the left, you see an example of finite memory prediction, where the prediction is conditioned only on the most recent states. In our recent work, we are able to prove provably bounded estimation errors for this type of approximation. Another popular technique is moment matching, which attempts to fit a Gaussian distribution to the distribution of the current state. We come back now to our original problem, design of the optimal controller via the stochastic program. We will see that our controller will have dual features. The first key ingredient here is the online learning aspect. The controller does not only depend on the parameter theta, but also on the whole history of data. As an example, consider a feedback linearization control where the system model is continuously improved online via learning. The theta then represents the feedback gain. The second key ingredient is the optimization over a time horizon larger than 1. Considering the online learning law in this stochastic optimal control problem incentivizes active learning, as long as it pays off in the long term by improving the control performance later on. So it makes the controller aware of the influence of its current actions on future observations. Hence, the learning is anticipated. The resulting control will have dual features. The exploration and exploitation trade-off is implicitly determined by the level of uncertainty in the model and the cost function. In order to compute the optimal control parameters, you would ideally like to compute this expected cost over all possible realizations of the GP model. This means that we have to compute this integral over multiple steps, but this is in general intractable. Therefore, we employ here a sampling-based approximation called sample average approximation. The idea is to draw a finite number of samples from the problem's probability distribution to substitute the integrand by a summation over the sampled scenarios. Here the idea behind sample average approximation is illustrated. We see 3 different trajectories sampled from the same prior distribution to obtain the approximation of the expected cost. So capital M would be 3 here. The optimization problem for the approximated cost is then deterministic and can be solved with the appropriate solver. Also note that the individual sample passes can be computed in parallel, while the optimization iteration is centralized. By exploiting now the properties of the GP, we are able to show that sample average approximation converges to the true optimum. The key features to prove this are the IID sample-based representation of the multi-step prediction for the GP dynamical model and the continuous differentiability of most interesting kernels. The result is an algorithm that provides a solution which converges to the true solution with probability 1 as the number of sampled scenarios increases. Here we see an illustration of how the approximate cost function converges with growing number of samples from the left to the right. In blue, we see the true cost function depending on the parameter theta. In red, it's the approximated cost. With only a few scenarios, here on the left, there's quite some difference between the true and the approximated cost. Yet the approximation error goes to 0, with m going to infinity. Now we look at the simulation example for illustrating the behavior of the control law. In particular, we will compare the performance between a controller with anticipating the online learning and a controller that disregards the online learning. We consider this nonlinear dynamics and this unknown function g. A Gaussian process with a squared exponential kernel was trained a priori with a small set of 100 training data pairs. In the picture here, you see the ground truth of the function g in red. The training data are depicted as black crosses, and the blue line represents the mean function, and the blue shaded area shows the standard deviation of the Gaussian process. We consider a tracking problem where the tracking error shall be minimized over 150 time steps. The controller is composed of a feed-forward term based on the Gaussian process mean and a feedback term parameterized by θ1 and θ2. The sample average approximation is applied here with 200 scenarios. Here on the left, we see the predicted optimal behavior if learning is not anticipated. In this case, the optimizer does not take any learning-induced control law updates into account. Shaded in gray is the area where prior training data is available. The state is depicted in blue, in red is the desired trajectory. As we can see, the control law barely attempts to track the desired trajectory, and the running costs that are shown at the bottom here in blue remain high. This is because learning is not anticipated. The uncertain region of the state space is expected to remain uncertain, and venturing into that region would only yield highly unpredictable behavior. Here the control is conservative in the sense that it avoids uncertainty, and it results in a rather poor performance. By contrast, if learning is anticipated, the controller attempts to track the desired trajectory, even though it means leaving the known region of the state space. This is because it knows that the model will improve eventually, and so will the control. There is a learning transient with high running costs in the beginning, where the controller explores. But already after 40 steps, the learning is complete. The controller starts to exploit, and the running costs become significantly lower. As a result, the total control performance is significantly improved. Now I would like to conclude the talk. We have considered the problem of active online learning control here with Gaussian processes. We demonstrated the issue related to multi-step predictions for GP dynamical models, which result in a non-Markovian dynamics. In order to address the computational complexity problem of the involved stochastic optimal control problem, we have considered a sample average approximation and show that it leads to an arbitrarily exact approximation of the optimal solution. Finally, as expected, the resulting controller enjoys dual features, implying that there is a learning-induced transient, but also an optimal trade-off between exploration and exploitation. Clearly, this is only a first step, and there are many open problems still, in particular in the challenging area of learning control with guarantees. Our current work concretely related to this problem concerns sample complexity guarantees and its application in receding horizon fashion. The issue of learning control with guarantees is also a larger topic at our chair, currently in conjunction with application in rehabilitation and underwater robotics. Apart from Alex, I would also like to particularly thank Jonas Umlauft, Thomas Beckers, and Armin Lederer for all their contributions in this exciting research area. Finally, I would like to mention that in addition to this work, we also have another contribution presented here in the Rapid Interactive session by Armin on confidence regions for simulation with learned probabilistic models. And with this, I would like to stop. I would like to thank you for your attention, and I look forward to an interesting Q&A session.